Today we will discuss the significance of oxidation numbers in ionic and covalent compounds. As we know, ionic compounds are compounds in which the type of bond between two atoms is ionic because it's formed between a metal such as sodium and non-metal such as chlorine atom here. Here the chlorine atom takes away the electrons of the bond towards the chlorine atom here, and the type of bond here is electrostatic attraction between the negative charge of the chlorine atom and the positive charge of the sodium atom. So in cations here, sodium in this case, it indicates that the sodium atom has lost one electron to the chlorine atom to form sodium ion and chloride ion. And for the chloride ion, it gained one electron so that it formed the chloride anion as we see here. So the significance of oxidation numbers in ionic compound, it explains how many electrons are lost or gained in the compound. For the covalent compounds such as HCl or hydrochloric acid, the type of bond here is covalent bond because it's formed between two nonmetals, the hydrogen nonmetal and the chlorine nonmetal. As we see here, but covalent compounds can be subdivided into two types or two main categories: polar compounds and nonpolar compounds. Polar, which have dipole moments such as HCl, and nonpolar, let me write it here, so this one should be polar. Something nonpolar and covalent at the same time, such as halogens, for example I2, Cl2, all of them are covalent but nonpolar. So in polar compounds such as HCl, let me write it this way, the electrons of the bond move towards the chlorine atom more than, or is displaced to the chlorine atom compared to the hydrogen atom here. So the chlorine atom here takes a partial negative charge, and the hydrogen atom here takes a partial positive charge. So chlorine atom partially negative should be partially negative here, and the hydrogen here should be partially positive. And if we assign oxidation numbers to such compound HCl, then hydrogen should be positive 1 and chlorine atom should be negative 1, because in covalent compounds the oxidation numbers indicate the displacement of electrons towards the more electronegative atom, and the positive charge in, or the positive oxidation number in covalent compounds, it indicates that the electrons is taken away from the the partially positively charged atom. So let's talk about some rules in oxidation numbers. So the first rule here is the oxidation state of the molecules in a reaction. For example, if you found in a reaction something like pure carbon or pure oxygen molecule or something like chlorine gas or nitrogen gas or hydrogen gas, like a molecule in its pure form, then the oxidation state you write it, the oxidation state here should be oxidation state is equal to 0. You have to also memorize some of the most common oxidation states, or fixed, I should be precise here, fixed oxidation states, such as what I will write now. So, for example, in most cases, hydrogen is positive 1, then lithium positive, then sodium positive 1, and potassium positive 1. Then we have something like magnesium 2 plus and calcium 2 plus, and here on the other side of the periodic table, aluminium 3 plus, and those for the metals, for the non-metals, and we also know that the main transition metals are located in the middle of the periodic table. So we move to the non-metals such as oxygen, 2 negative, in most cases 2 negative, and before it nitrogen 3 negative, and then fluorine 1 negative, chlorine 1 negative, bromine 1 negative, and iodine 1 negative. So for the only elements that I will draw a circle at, they have always one oxidation state. These are their oxidation states. These elements only, you see, and the rest of elements have different oxidation states, but they are generally like they take the drawn oxidation state on the board. So you will not be perfect at assigning oxidation states without practicing. So let's take some examples, such as let's say H2SO4. This is sulfuric acid. No. Here the hydrogen should be positive 1 oxidation state, and oxygen, each oxygen should have negative 2 oxidation state. Then we say 2 positive, 2 hydrogen positive, because the number of hydrogens here are 2, positive 2 plus S. S is the unknown. I'm assigning the oxidation state of the sulfur atom here, minus 8 is equal to 0. Why 0? Why 0 here? Because the net charge of the whole compound of the sulfuric acid is 0. Then simple math, and we can calculate the oxidation number of S. So S negative 6 is equal to 0. Then S is equal to positive 6. Let's take another example. HClO4. This is perchloric acid. You see here the hydrogen most likely is positive 1, and the oxygen here -2 oxidation state. Then we have 1 plus Cl -8 or -8 is equal to 0. Then we have positive 1 and -8. That means Cl -7 is equal to 0. Then the Cl is equal to positive 7. So here's something like K2 Cr2O7, or write it correctly. This is potassium. This is potassium dichromate. Potassium dichromate. Let's calculate the oxidation number of the chromium atom. Here the potassium should be positive 1. Each potassium atom should be positive 1. And each oxygen atom should be -2. Then we have positive 2 plus 2Cr minus 14. Minus 2 times 7 is -14. Okay? The whole compound should be 0. Okay? The net charge, I mean. Okay? Then we have plus 2 minus 14. That means 2Cr minus 12 is equal to 0. Then 2Cr, 2 chromium atoms, is equal to positive 12. Then each chromium atom is equal to positive 6. Let's see the oxidation state of another common oxidizing agent. This is a very common oxidizing agent, potassium dichromate. Then we have something like KMnO4. This is potassium permanganate. Potassium permanganate. Yeah, potassium permanganate. It was written in a bad form, sorry, but yeah. We have potassium here, which is positive 1, and each oxygen atom should be -2. Then we have 1 plus manganese, which is the unknown, is equal to, no, sorry, minus how much or how many? How many? Minus 2 times 4. Each oxygen atom its oxidation state is equal to -2. -2 times 4, that means -8. That should be equal to 0. Then manganese minus 7 should equal 0. Then manganese should equal at the end positive 7. So let's discuss the oxidation state of the polyatomic groups. So let's discuss the oxidation states of the polyatomic groups. Polyatomic groups such as OH and something like SO4, sulfate, hydroxide, sulfate, phosphate, something like nitrate, something like carbonate. Excuse me, my voice is not the best today. Something like NO2, yeah, nitrite, and finally NH4. The hydroxide ion, its oxidation state should be -1, sulfate 2 negative, PO4 3 negative, nitrate 1 negative, carbonate 2 negative, nitrite 1 negative, NH4 or ammonium group 1 positive. Okay, maybe we can add something like this, the chlorate. These are the most famous anions and cations uh, as polyatomic groups. Okay, so let's take some examples. Something like AlCl3. We already know that the oxidation state of the aluminium is +3, and this compound should equal to 0 as a net charge. Its net charge should be 0. Then each chlorine atom, or here in the anion form, each chloride anion should be -1. Then we have something like another compound, MgSO4. We can calculate, I want to calculate the oxidation state of magnesium. We know that the oxidation state of the sulfate group is 2 negative, right? 2 negative. Then the magnesium should be 2 positive, so that the total oxidation state is equal to 0 of the whole compound. Let's move to another example. Something like this. Potassium nitrate. You see potassium nitrate here, right? So potassium, or the nitrate anion, we all know that the nitrate polyatomic group, its charge is, or oxidation number, is equal to -1. Then the potassium should be +1. So the whole charge on the whole compound carries 0 charge. Okay. So another rule here is fluorine atom always carries -1 oxidation state, no matter what element. Let's see. For example, HF, the oxidation state on the fluorine atom should be -1. Why? Because we have HF, like here in this formula. The fluorine atom is always more electronegative. Another compound should be KF. We all know that the fluorine atom is more electronegative than potassium, so it should carry -1 positive charge and the potassium +1 oxidation number. Okay, then something like this, and this is tricky. So what is the oxidation state on the oxygen atom? To your surprise, that the oxidation state of the oxygen atom should be +2, and this is the only case in which the oxygen atom is or has a +2 oxidation state. Why? We can look at the structural formula here, and we can see that the fluorine atoms are pulling the electrons of the bonds towards them, as you see here, and this will lead to introduction of partially negative charge, and this is partially negative as well, and you will have here 2 partial positive charge on the oxygens, right? So in total it will be -1 oxidation state on each fluorine and 2 positive charges, 2 positive oxidation state on the oxygen.